This video covers how we create time series of volatility and how they are useful when we want to do backtesting of VAR models later in this module. We'll do that in topic 8. So let me share my screen. And yeah, the relationship between VAR and volatility is one-to-one in the case of a normal model or any other model, like a student T model, and any model of value at risk in which standard deviation is the main driver of VAR. So by looking at time series of standard deviations, we can get time series of VAR, which we can put into the backtesting, which I mentioned we're going to do at the end of this module. But standard deviations are most commonly quoted as volatilities. That's the annualized standard deviation. It corresponds to an amount that we could lose with a certain probability over a 1-year horizon. It gives the standard deviation of the annual returns, and plus or minus 1 standard deviation is a confidence level of like 65% sure. So if you say the volatility is 20%, then you would say that over the next year you are around 65% sure that you'll make or lose 20% of the current portfolio value. Or it's around 2 for plus or minus 2 is like the 95%, 1.96 really, but plus or minus 2 is the 95% confidence interval. So we can say that if the volatility is 20%, that we're 95% sure we won't lose more or gain more than 40% of the current volatility, the current portfolio value. So just recap from topic 3 so that this annualization process is clear in your head. And we've done it earlier as well in this topic, but I said I would get back to it later in this lecture, so I'm doing that now. Volatility is the annualized standard deviation of the returns. So to annualize the standard deviation, we normally assume 250 trading days a year. Some countries have 252 trading days, others have less than 250, but 250 is a nice round number. So I normally assume that, but you can't do that for crypto markets. You have to have 365 days for the annuals. And if it's like over a 2-week horizon, instead of 10 trading days, you would have 14 trading days for crypto. Anyway, so the square root of time rule, if you remember, it's based on the assumption that returns are IID, independent identically distributed. And so if you have daily returns that are IID, they have mean, mu1 and sigma1 is their standard deviation. And then we can scale the mean and standard deviation from a daily mean to be the mean of h-day returns multiplying by h. And similarly, we can scale the standard deviation of the daily return to be the standard deviation of an h-day return. And of course, the standard deviation will always be bigger for the range of a distribution over 10 days is always bigger. The uncertainty is bigger over 10 days than it is compared with 1 day. So again, you scale up to go to longer risk horizons, but you only scale by the square root. The variance and the mean you scale by the h, the holding period, but for the standard deviation, you scale with the square root. So if we have a volatility, then we can divide by 250 to get the daily standard deviation. But if we wanted the 10-day standard deviation, we wouldn't divide by 250. there's 250 days in a year, but how many 10 days are there in a year? Well, we divide by square root of 25 because there are 25 10-day periods in 250 trading days. And the square root of 25 is 5. So for example, if you've got a volatility of 20%, then that would convert into a 10-day standard deviation of 20% or 0.2 divided by 5, which is 4%. Now, to calculate historical volatility, we take a very large sample of returns, 6,000 returns I've got in the spreadsheet or more. But then we fix a window size, which could be much smaller. It could be like 30 or 60 or 90 of the usual timeframes. So we might take just 30 of the returns. So we start in 2020 at the beginning, and we take the first 30 returns. And then we roll the window by adding a return and dropping one off. So we drop off the 3rd of January 2020 in the spreadsheet, but we add one more at the other end. So we've always got 30 returns. And every time we fix the window, we then calculate the standard deviation. And then we can annualize it into a volatility if we want to report it as a volatility. Because these are daily returns, so we're going to get the sigma 1 from that calculation. If they were 2-day returns, we'd get sigma 2 from the standard deviation calculation. If they were monthly returns, we would get the sigma monthly from the standard deviation calculation. Anyway, so we roll the window every time we calculate the standard deviation, and then we use the square root of time rule to get the volatility. And this is the result. We'll go through this in the spreadsheet, in the calculation. We can see that the S&P 500 volatility is around 15%, but sometimes it can be more or less. In particular, when you have some extreme event, for example, here in April 2022, the 30-day volatility jumped up much more than the 60-day volatility. But that's based on a standard deviation of the last 60 returns. But then the 30-day didn't stay up quite so long. So we'll go through the reasons for that when we look at this spreadsheet. Now, for exponentially weighted average moving, exponentially weighted moving average, UMA is quicker, the volatility. Instead of equal weighting of the past returns, because the standard deviation is just equal weighting, right? You take the variance as the sum of the squared last 30 returns. Assuming the mean is 0, you wouldn't divide by n minus 1 by 29. You divide by 30. You only take 1 off when you have to use these squared mean deviations. But if the mean is 0, you assume the mean is 0. You haven't got to estimate that mean parameter, so you don't lose a degree of freedom. So you can divide by n. So for the historical, we get the variance as the sum of the squared last 30 returns divided by 30. And this formula here, you've got the last, well, you've got more than 30. It goes on forever, actually. I mean, we could stop at 30. We could say RT minus 1 squared, RT squared, they're all squared, all these returns are squared. We could go RT minus 4 squared, and so on and so on. But the point is that instead of weighting each one equally, so we've inserted this weight lambda, which is less than 1. So lambda might be, say, 0.9. So we would take the return that we just observed, RT squared, today, and yesterday's return squared, but only 0.9 times that, and then only 0.9 squared, which is 0.81 times the day before squared, and then even smaller and smaller and smaller. This lambda to the power 10 is more or less 0 if lambda is 0.9. So that's why I don't stop here. But the weights are now different. They're exponentially decaying because they get smaller and smaller. 0.9, 0.9 squared. It doesn't have to be 0.9, of course. It could be any number between 0 and 1. Typically, it'd be around about 0.95 or something like that. quite high actually. We can change it in the spreadsheet, you'll see the effect. So, well, we have to divide by the sum of the weights. In an historical model, the weights were equal. So if we had 30 returns, we'd have 1 plus 1 plus 1 plus 1 30 times. So we divide by 30. Whereas here we have to divide by 1 plus lambda, lambda squared, lambda cubed, etc., etc. That's the sum of the weights. Now, it's very difficult to program this in Excel, but the formula that we put into Excel is this recursive formula that you can see here. So the Yuma variance, obviously we square root it and annualize to get the volatility, but the Yuma variance is 1 minus lambda times today's return squared plus lambda times yesterday's variance, which is easy to compute. We just have to start off with some value for sigma hat 0 here, okay? And then we can get sigma 1, and we can put sigma 1 in there to get sigma 2, and every time we add on the returns we've just observed. So how do we prove that? Well, those of you who have done maths will know that 1 plus x squared plus x cubed plus x to the fourth is 1 over 1 minus x. So 1 plus lambda, lambda squared, lambda cubed is 1 minus lambda to the minus 1. Now, remember this formula here, that's just copied from the previous slide. That is the formula we use for exponentially weighted moving average. But using this, we've got 1 minus lambda to the minus 1 as the denominator here. But it's to the minus 1, so it goes on top with the numerator. So we've got 1 minus lambda times this thing on top. All right, now the next line, we're going to take this r squared and put it with 1 minus lambda there. And then look at the rest. We've got lambda in every term. So we can take lambda out as a factor. We've still got the 1 minus lambda. And that gives us rt minus 1 squared. And instead of lambda squared times rt minus 2 squared, we've got lambda times rt minus 2 squared. And lambda squared times rt minus 3 squared, and so on and so on. But forget the lambda here, the 1 minus lambda times rt minus 1 squared plus lambda rt minus 2 squared, that, compare it with the line above, it's very, very similar to the line above, except the line above we've got rt squared, but here we start with rt minus 1 squared. So this factor here must be sigma hat t minus 1 squared, and that proves the formula. And here's an example of the Yuma volatility for two different values of lambda, 0.94 and 0.97. I've chosen those because they're used by a standard database that sells volatility data called Risk Metrics. And so you can buy data on the volatilities of your risk factors, 500 or so or more different types of risk factors. Every day you get values for their volatilities, and you can get time series of their volatilities, but you have to convert them into standard deviations in order to put them into the Savart formula. And so let's have a look at the comparison of the Yuma and the historical as well. I'm going to finish this video with looking at the Excel spreadsheet. So where are we? Here's the Excel spreadsheet. Historical volatility. Okay, so we've got the S&P 500 data that we had before. We've got the returns that we had before. And for the 30-day, let me just blow this up so you can see. Okay, so clicking here, I just take the standard deviation of the last 30 returns and annualize it. Because these are daily returns, I use square root of 250. And the same formula, this C2 to C31, that's the last 30. If I simply drag it down, it will automatically change it to C3 to C32, so that the, let me click on this, and you can, well, column C will be starting now on the 4th of, so we start on the 4th and then we go on because we haven't got a return there. Okay. And for the 60-day, we do the same thing. We actually include that 0 return. And then the next one, we go from C3 to C62. And the next one, C4 to C63. So that's the rolling window. And the graph looks like this. Now, as I mentioned this feature, let me just go in and create some crazy return. I'm going to change the return. I'm going to go to, I don't know, down here. It's not right at the beginning. And I'm going to produce a very sort of negative return. So minus 0.07. That should be big enough. Okay, so here in the graph, you'll see that there's just one return which makes the 30-day volatility jump up to 25% and the 60-day volatility jump up to 20%. Why? Well, when we look down here, the jump in volatility is created by this one return. But, so it jumps up because that return just goes into the sample. C86 is in the sample. And C86 is still in the sample down here. And it's got equal weight. Doesn't matter that it was a few days ago. It's still in the sample here, even though it occurred 2 weeks ago. And likewise in the 60-day sample, but it eventually drops out. Here it's just about in the sample. It's the very last return in the sample. And then it drops out. It's no longer in the sample, but it's still in the 60-day sample, which goes back much, much further, as you can see. So what's happening is that you've got just one return, which is staying in the sample with equal weight for exactly 30 days. And it's higher because you're averaging, you've got your standard deviation over 30, whereas here you've got standard deviation over 60. So that one return has less of an effect because you divide by 60, not 30. So the jump up isn't so much, but what happens, you get this sort of ghost feature because suddenly 30 days after that return in June, the volatility jumps right down. Nothing happened on that day. It's like a ghost of what happened on the 30th of June. Or whenever it was, where did I put it? April. You know, I've just put it in on a particular day. And then 60 days later, it jumps down. So it's a very bad model of volatility. We shouldn't really be using historical volatility. The Yuma volatility does not have that problem. So we could put in a large return somewhere. And okay, so let me just go through the calculation first of all. We've got the data on the index, we've got the returns, usual way. Oops. And I've got to have a starting value for sigma 0. Okay. And so this is with a lambda of 0.94. This is the recursive formula on that slide. It's 1 minus lambda is 0.94, times the return squared, that's C3 squared, plus lambda times yesterday's variance. So VAR is not value at risk, it's the variance. And with a different parameter, we just change the parameter there. And once we've typed in the formula, we can just fill down and this C4 will change and D3 will change. The next one, it's C5 and D4 as T goes through running time. So these are the variances, and for the exponentially weighted moving average volatility, I need first of all to take the square root of the variance to get the standard deviation, and then I need to multiply by the square root of 250 to get the volatility. So I do that for both series, and that's what you see in the plot here. Now, If I go into a return somewhere down here and make it minus 0.07, a big negative return, as we did before, what is the effect? Well, the small lambda jumps up a lot, but then decays quickly. The large lambda, the 0.97, jumps up less, but decays more slowly. But the point is, you don't have that cliff edge. It doesn't suddenly jump down on a day when nothing happened. But the persistence in this volatility spike depends on the lambda. The higher the lambda, the slower the decay. And that's why it's called the decay constant. Some people also call it the smoothing constant, because another thing you observe is the higher the lambda, the smoother the volatility series. Okay, so let's have a look at the comparison of these two volatilities. Now, in this spreadsheet, we can change the value of lambda. I've put it in as a parameter. Remember, anything that is red, you can't change. So this is the variance. And it's got it's this formula here. We've got volatility comparison there with an exclamation mark. It just means it refers to this spreadsheet. But if you want to refer to a parameter in another spreadsheet, you have to have the spreadsheet name in inverted commas, followed by an exclamation mark. We don't really need it here because it's in the same spreadsheet. It would still work without that volatility comparison exclamation mark there. And then the historical 30-day, I'm just copying from the historical. And we've got some funny parameters here because I changed them. Where are we? Square root volatility comparison there. Okay, so here's the var, here's the historical, and you can play around with this spreadsheet with different lambdas. Finally, converting an historical volatility to a value at risk should be fairly straightforward by now. For example, I'm taking a 30-day standard deviation here. Okay, just take the standard deviation, and I'm going to change it into a var using the norms inv and the square root. The square root would change it to whatever from daily to 10-day standard deviation or 10-day to annual standard deviation, i.e. volatility. What are the parameters G1 and G2? Well, G1 is the significance level. So if I change the significance level, maybe do 5%, oops, 5%, you see everything shifts down because the var increases with the confidence level, not with the significance level. If I do 0.1, it shifts right up. The scale changes every time. Similarly, the risk horizon here will change. It'll be lower for a lower risk horizon, and try and do an annual, it'll be this. Okay, I think that's enough for this demonstration. Take a look at the Excel spreadsheet, and I'll see you in the next video. Bye for now.